Welcome back. I have a structure here that we call a frame. A frame is a structure that is composed of multiple parts. You can see that this one here has 3 members. They are all connected with pins at B and D. The frames are used to support loads. There is another type of structure called machines. For example, a robot arm is a machine. Just like a frame, it also consists of several parts. The difference between frames and machines is that a frame is supposed to remain in one configuration while it supports loads. However, machines change their configuration to alter the effect of forces. You can imagine that as the robot arm changes its position, the loads that the arm's 3 members experience will vary. And now, if you look at our frame, you can see that it is subject to 2 downward vertical forces and a couple moment. It also has a fixed support at A and the roller supports at C and E. The relevant dimensions are in the image, and you can also neglect the weight of the structure. And now, your task is to find the reactions at points A, C, and E. Good luck, try it out yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. Let's now find the reaction supports at A, C, and E for our frame. First of all, your initial intuition might be that we have improper constraints. After all, you have pins at B and D. So if I apply a 10 kilonewton meter couple moment to the member BD and a downward 10 kilonewton force to member DE, then shouldn't the equilibrium be broken where pin D moves down? Because remember, these pins only resist translation, not rotation. The answer is no, and here's why. If pin D goes down, then pin B needs to move up, because we have a rigid body assumption. But because the pins resist translation, member AB also needs to become diagonal. However, that cannot happen because you have a fixed support at A which resists rotation, and member AB cannot be bent because it's rigid. If you had a pin at A as well, then it would have been a different story. Then member AB could rotate about pin A. However, that's not the case here. We have a fixed support at A. Therefore, member AB remains horizontal. But that means that members BD and DE also need to stay horizontal. Therefore, there is equilibrium, and you do not have improper constraints. You have proper constraints. And so, let's include all our forces and moments to our free body diagram. Besides the 2 external forces and 1 external moment, you also have AX, AY, and MA, and then CY and EY. The 2 roller supports give you 2 vertical forces at C and E. The fixed support at A gives you AX, AY, and MA. But now we have a problem. As you can see, we have 5 unknowns, but we can only have at most 3 equations from our 3 rigid body equilibrium principles. The sum of the forces in the x direction must be 0, the sum of the forces in the y direction must be 0, and the sum of the moments about some kind of point must be 0. So we cannot solve this system in this form. However, we can solve it by disassembling this structure into its individual members, just like we did it in one of the previous examples. Since the entire structure is in equilibrium, each individual member also needs to be in equilibrium. Let's take the member DE and only draw a free body diagram for that member. You have a 10 kilonewton force down, then EY due to the roller support, and then DX and DY. This is a pin support, so rotation is allowed, but translation is restricted in all directions. Note that we did not draw DX and DY on the free body diagram that was drawn for the entire three-member structure, because in the general free body diagram, dx and dy are internal forces. If you look at the members BD and DE, then at D, both members have dx and dy, but they are in the opposite directions because of the Newton's third law. Thus, they cancel each other out. That's why we don't include them in this general free body diagram. However, if you draw a free body diagram for the member DE only, then dx and dy become external forces and you have to include them. And now in this free body diagram that you have only for the member DE, you only have three unknowns. Now you can solve for them. The sum of the forces in the x direction must be 0. You only have one force there, so dx equals 0 kilonewtons. Then you do the same thing for the y direction. This is the equation, so dy equals 10 minus ey. Now from symmetry you already know that because of the fact that this 10 kilonewton force is vertical and it's applied to the middle of this member, then of course your ey will be 5 kilonewtons and dy will be 5 kilonewtons. But let's find them formally. So I'm going to take a moment. About point D, their sum has to be 0. So this will be the equation. So you have 3 ey equals 15. And so ey equals 15 over 3. And that's 5 kilonewtons. And now here you can see that dy equals 10 minus 5. It's 5 kilonewtons. And so you have dx, dy, and ey. Now we can take the member BD and draw the free body diagram for it separately as well. So this is the couple moment. This is the roller support. At B, you also have reaction forces in two directions. Here are the dimensions. And now this is very important. Extremely important. Since in the free body diagram for member DE, your dx pointed to the right and dy pointed up, in the free body diagram for member BD, your dx must point to the left and dy must point down. Remember, when you put those two members together, dx and dy forces become internal forces and they have to get cancelled out. It's very important that you do it or you get a wrong answer. And so again, we have three unknowns here. You already know what dx and dy are, so your unknowns are cy, bx, and by. And so let's find them. The forces in the x direction will give you this equation, so bx equals dx. Since you already know that your dx equals 0 kilonewtons, that means that your bx also equals 0 kilonewtons. Then the forces in the y direction must give you this equation, so by equals dy minus cy. And then let's take the moments about point B. That will be your equation. You know that your dy is 5 kilonewtons, so you have 3 times 5 plus 10. That gives you 25. Then cy equals 25 over 1.5, that's approximately 16.7 kilonewtons. And so now you can find your By, which is dy minus cy. So 5 minus 25 over 1.5, that's minus 35 over 3 kilonewtons. It's negative, so it means that in reality, By points down. And now, there are two ways how you can find the remaining reactions Ax, Ay, and Ma. We can draw a free body diagram to the member AB. Even though your By was negative, on the free body diagram for the member BD, it still pointed up. So now for the member AB, it needs to point down. Also, Bx now points to the left because it pointed to the right for the member BD. And then of course you have this 9 kilonewton force here, and then you have Ax here, Ay, and Ma. And with regards to these internal forces at pins B and D, think of it this way. You have 3 different free body diagrams for 3 different members. When you put all these 3 body diagrams together, all the internal forces need to cancel out. Bx, By, dx, and dy. They all need to cancel out, otherwise the Newton's third law is violated, and that cannot happen. And so now that you know your Bx and By, let's find Ax, Ay, and Ma. This is forces in the x direction, so Ax equals Bx. Since Bx equals 0 kilonewtons, also your Ax equals 0 kilonewtons. Then the forces in the y direction, they give you this equation. I can rewrite it like this, Ay equals 9 plus By. And now remember, your By was a negative number, and so you have to put this negative number here, minus 35 over 3, and so you get minus 8 over 3 kilonewtons, or minus 2.67 kilonewtons. So that's your Ay. And then finally, I take moments about point A. This is my equation, and so I can write that Ma equals, and then all this, so I have 13.5 plus 3 times minus 35 over 3, and that gives me minus 21.5 kilonewton meters. Remember, By was negative, so you have to make sure it's negative here as well. And also your Ma is negative. It means that in reality, Ma is in clockwise. Finally, Ay is negative, which means that in reality it points down. Now alternatively, you can get Ax, Ay, and Ma using the general free body diagram for the entire structure. After you find Cy and Ey, and Cy is this one here, and then Ey is this one here. And you can do that because once you know your Cy and Ey, in this general free body diagram, you will only have 3 unknowns, Ax, Ay, and Ma. So once you know your Cy and Ey, you can write the sum of the forces in the x direction. That gives you Ax equals 0 kilonewtons. Then the sum of the forces in the y direction, that's this equation. So you can write that Ay equals 9 minus Cy plus 10 minus Ey. So you have 9 minus, and then Cy was 25 over 1.5 plus 10 minus 5, and 5 was Ey. And so you get minus 8 over 3 kilonewtons. Finally, let's take the moments about point A, and so that's the moment equation. I can write Ma equals, and then all this I know that Cy equals 25 over 1.5, Ey equals 5, and so in the end, Ma equals minus 21.5 kilonewton meters. As you can see, in both cases, you get the same answers. Whether you take this AB member separately or you take this entire global structure, you get the same Ma, minus 21.5 kilonewton meters, just like here. Then you get the same Ay, it's minus 8 over 3 kilonewtons, and here as well, minus 8 over 3 kilonewtons, and also Ax equals 0 kilonewtons, and also here it equals 0 kilonewtons. So it's your choice whether you take this approach or this approach. That's how you solve problems concerning frames and machines. Thank you very much. Welcome back. I have a pulley system here. It keeps a small cargo elevator in equilibrium. The mass of this elevator is 50 kilograms. Its center of gravity is the center of the elevator. You can neglect the weight of the pulleys and the cables. And so, my question to you is, how much force P do you need to apply in order to keep the elevator in equilibrium? You can assume that G equals 9.81 meters per second squared. Try it out by yourself first, and then see the solutions in the next video. Thank you. Welcome back. Let's now solve this pulley system and find how much force P we need to apply to keep the elevator in equilibrium. First of all, the mass of the elevator is 50 kilograms. Thus, Fg equals 50 times G newtons. The other thing is that, remember, cables transmit force along the cables. So if I pull at P newtons on the left side of pulley A, then the same force will be transmitted along that cable. So if I cut the remaining two downward cables in my mind from pulley A, then first of all, I will have the same force P on the other side of pulley A, and due to Newton's third law, I have that force P on the right side of pulley D as well. Since cables transmit loads directly, you also have P on the left side of pulley D. And then due to Newton's third law, you also have P from pin A downwards. Now the force that goes from pin A upwards, we can call it B. If I cut all the three cables from pulley B that are below it, then again, force B will get transmitted around pulley B and pulley E. So from pulley E, you have two upward forces that are both B. And due to Newton's third law, you have the same B forces on the other side. And also here, you have this B force. Finally, the force that goes from pulley B upwards, we can call it C. Again, the same thing. Force C transmits along the cable around pulley C and F. We mentally cut all the cables below pulley C, and you can see that you have C forces below pulley C and above pulley F. And now, let's only draw a free body diagram to pulley A. You have 3 P forces here and 1 B force here. Let's apply the rigid body equilibrium principle to it vertically. B minus 3 times P equals 0. So B equals 3 times P. Let's do the same thing for pulley B. You have 3 B forces here and 1 C force here. So all the forces in the y direction, they have to be 0. So you have C minus 3 times B, that's 0. C equals 3 times B, but since B equals 3 times P, you know that C equals 3 times P. So it's 9P. Finally, let's draw a free body diagram for the elevator only. This is our elevator. This is the force of gravity, 50G, and these are all the upward forces. Let's again apply the rigid body equilibrium principle here. All the forces in the y direction, their sum has to be 0. So you have 2 times P plus 2 times B plus 2 times C minus 50G equals 0. However, since B equals 3 times P and C equals 9 times P, I can rewrite this equation like this. 2 times P plus 2 times 3 times P plus 2 times 9 times P minus 50G equals 0. In other words, you have 2 times P plus 6 times P plus 18 times P equals 50G. In total, you have 26P equals 50G, so P equals 50 over 26 G newtons, or 25 over 13 G newtons, or approximately 18.9 newtons. And there you go. To keep the elevator in equilibrium, you have to apply approximately 18.9 newtons of force on the left side of pulley A. Note that the force of gravity of the elevator is 50 G newtons, which is 490.5 newtons. That's a lot for one person to pull. However, as you can see, with the right pulley system, you have to apply significantly less force in order to keep it at rest. In this case, you only have to apply 18.9 newtons of force in order to keep a 490.5 Newton object in equilibrium. That's equivalent to holding something that has a mass of 18.9 over G, or 18.9 over 9.81, 1.927 kilograms. So approximately 2 kilograms. That's a lot easier to manage. That's what pulley systems are for. Thank you very much. Welcome back. I have another pulley system here. The cargo experiences the force of gravity of 150 G newtons. The mass distribution is uniform. You can neglect the weight of the pulleys and the cables. And so my question to you is, how much P force do I have to apply on the right side of pulley C in order to keep the system in equilibrium? Again, it's important that you give it a try on your own first and then see the solutions in the next video. Thank you. Welcome back. This problem is very similar to the previous one. This force P gets transmitted about pulleys C and D until it reaches the pin at E. If I now make these imaginary cuts, then due to Newton's third law, you will have a P force here, and also here, and here. The force above pulley C, we can call it B. It gets transmitted about pulley B and A. Again, if I make these imaginary cuts, then I will have B forces here, and then also between pulleys B and A, and pin E and pulley A. Let's now draw a free body diagram for pulley C. You have two P forces here and one B force here. You can apply the equilibrium principle. B minus 2 times P equals 0. So B equals 2 times P. And now let's draw a free body diagram to the cargo with pulley A. So you have 150 G newtons here, and then you have 2 B forces here. And so this is the equilibrium equation. 2 times B minus 150 G, that gives you 0. So 2 times B equals 150 G. However, B equals 2 times P. So you have 2 times 2P equals 150 G, or simply 4 times P equals 150 G. So P equals 150 G over 4. It gives you 37.5 G newtons. In other words, it gives you 367.875 newtons. There you go. You have to approximately apply 368 newtons to keep the system in equilibrium. That's way less than the weight of the cargo, which is 1471.5 newtons. Again, the pulley system simplifies your life. Thank you. Welcome back. Let's do one more pulley problem. You have two different configurations here. A person stands on a platform C. That platform is connected to these two pulleys, but in each case, the configuration is different. Platform C itself experiences the weight of X newtons. Its center of gravity is in the middle of the platform. A guy whose weight is 875 newtons is standing on the platform. The platform also applies normal force to the guy. In order not to slide down and keep the system in equilibrium, in the first case, case A, the guy has to apply force upwards to the bar AB. And then in the second case, case B, the force needs to be applied downwards to that bar, because now you have a different configuration. So let's call these two applied forces F1 and F2. You can neglect the weights of the pulleys and the cables. There is symmetry about the vertical axis, so there is no rotation. You only have to think in terms of vertical forces. So F1 equals F2, and they have equal distance from the center of the rod. And so my question is, what are F1, F2, and the normal force in each configuration? Since the platform has X newtons of weight, all the answers will be as a function of X. Let's see which configuration makes the guy's life easier and which one harder. Try it out by yourself first, and then see the solutions in the next video. Thank you. Welcome back. So let's now find F1, F2, and the normal force for case A and B. In order to solve this problem, we have to separate the guy from the system and draw a free body diagram only for him. Let's first take case A. You have his weight, which is 875 newtons, and it points down. Then platform C applies the normal force to the guy upwards. Since the guy applies F1 and F2 to the bar AB upwards, due to Newton's third law, the bar AB applies F1 and F2 forces to the guy downwards. Now let's draw a free body diagram to the rod AB. Forces F1 and F2 go upwards from the guy. However, the bar is in equilibrium. So due to symmetry, the cables from pulleys D and E apply forces F1 and F2 down. Then we draw a free body diagram to the pulleys D and E. You already know that the cables transmit forces along the length of the cables. That's why you have F1 and F2 forces on both sides of the pulleys upwards, and since they are in equilibrium, you have 2 times F1 and 2 times F2 pointing down. for pulleys D and E respectively. Finally, let's draw a free body diagram to the platform C. It has its own weight, x newtons. Also, since it applied a normal force to the guy upwards, due to Newton's third law, the guy applies the same force to the platform but downwards. And the Newton's third law is also the reason why you have 2 times F1 here and 2 times F2 here. Because in the pulleys, you have it here and here. And if you mentally cut these 2 wires, then you would have 2 times F1 here from both sides and 2 times F2 here from both sides. All that keeps the platform in equilibrium. And now, let's use the equilibrium principle on this platform C in the vertical direction. You would have this equation from platform C. Since F1 equals F2, you can just call it F. Thus, you have this equation here, or this one here, and so your normal force equals 4 times F minus X. And then we apply the equilibrium equation to this guy as well. So you have this equation here, so this is F, so this will be your equation now. Since you know that N equals 4F minus X, you can replace this N with that, and so you will have 4F minus X minus 875 minus 2F. That will be 2F minus X minus 875, and that will be 0. So 2F equals 875 plus X. You can take this 2 and you can put it here, and so F equals 437.5 plus 1/2 times X. That means that this N here, it equals 4 times F minus X, or 4 times all this minus X. In the end, that will give you 1750 plus X newtons. There you go. For configuration A, F equals this thing here, that's your F, and N equals this thing here. Since F1 equals F2 equals F, this F here, it's F1 and F2. Remember, F is the force applied by one hand only. That means that the total force that the guy needs to apply to the rod is the following. F total equals 2 times F, or 2 times, and all this, which is 875 plus X newtons. Welcome back. So we have found the total force upwards applied by the guy and the normal force that the platform C applies to the guy for case A. But what about case B? Well, while the configuration is different, the way you approach the problem is the same. You first draw a free body diagram only for the guy. The only difference now is that since the guy applies downward forces to the AB rod, the AB rod applies F1 and F2 forces to the guy upwards. But you still have the guy's weight, which is 875 newtons, and it points down. And then the platform C applies some kind of normal force to the guy upwards. Then we draw a free body diagram to the AB rod. Again, the rod is in equilibrium. The guy applies F1 and F2 forces downwards to the rod, and then the cables from pulley D and E, they apply those forces upwards, respectively. Everything is upside down compared to case A. The next step is, of course, to draw the free body diagrams to the pulleys D and E. Again, everything is upside down. Since they are in equilibrium, pulley D has F1 force down on both sides, and you have twice of that force upwards, and the same thing for pulley E. Finally, we draw a free body diagram to the platform C. You have the weight of the platform, also the normal force applied by the guy due to Newton's third law. However, the difference now is that the rod C is balanced with F1 force on one side and F2 force on the other side. In case A, you had 2 times F1 on one side and 2 times F2 on the other side. Therefore, for case B, we have this equilibrium principle. Since F1 equals F2 equals F, you will have this equation, or simply this equation, or simply N equals 2 times F minus X. Then, let's write the equations for the guy. The guy is in equilibrium, so you have this equation. This is F, so you have 2 times F plus N minus 875 equals 0. So you have 2 times F plus 2 times F minus X minus 875, and that will give you 0. You can rewrite this equation like this. And so force equals 1 over 4 times, and then all this, and you're left with F equals 218.75 plus 1 over 4 times X. Then remember, this is your normal force, and now you have your F, so your normal force equals 2 times your force minus X. So N equals 437.5 minus 1/2 times X. And now this F here, it was a force applied by one hand. Thus, F total equals 2 times F, and that gives you 437.5 plus 1/2 times X. That's the total force that the guy applies to the AB rod downwards with his two hands. And there you go. You have your answers. This is for case A, and this is for case B. You can see that the configuration B makes the guy's life a lot easier. If we neglect the weight of platform C, so X equals 0 newtons, then F total for A would be 875 newtons, and the normal force for A would be 1750 newtons. And then for B, the total force would be 437.5 newtons, and NB would also be 437.5 newtons. So, in case A, the guy needs to apply the total force upwards that is equal to its own weight, and then the normal force that his body experiences is 2 times his weight, because 875 times 2 is 1750. In case of B, he only needs to apply a downward force which is half of his weight. So 875 over 2 is 437.5 newtons. Also, the normal force is half of his weight. However, if we say that the weight of the platform C is, let's say, 150 newtons, well then in case A, these would be your numbers, and in case B, these would be the numbers. In case A, both F total and the normal force increase, making it worse for the guy. In case B, he needs to apply a bit more force down, but the normal force actually decreases with the platform's weight. In any case, configuration B makes the guy's life way easier than configuration A. Now you can see how much the right pulley configuration matters. Thank you.